So today we are going to start our next unit, which is actually kind of a 3-unit span, so to speak, as the next 3 units is going to cover pretty much all things triangle related. Now, the reason I've broken it up into 3 separate units, some of them are smaller than others, which means that we'll have a test a little bit sooner, but that means that that test will be significantly smaller. Meaning not as much to have to memorize or keep track of. So our first one is going to be more of an introduction to triangles, some of the classifications, some of the more basic rules that are really just kind of day-to-day things that you would use, maybe in the real world. And then the next unit, unit 3, will be triangle congruence, meaning how can we tell 2 triangles are congruent to each other, meaning exactly the same. And then triangle similarity, yes. And then the 4th unit is going to pick up a topic called trigonometry. Now, trigonometry usually sounds scary. A lot of the times it's paired with classes like pre-calculus. We're not going to get into the more advanced things, but we are going to learn about trigonometry to the sense that we could calculate things further involving triangles. All right. So first thing, like I said today, we're going to focus on the classification. There's lots of ways to identify triangles based off of different aspects, that make each of them unique. So first thing we're going to look at here is classifying them by angles. So this is just going to be a little kind of bit of notes, to a reference guide, so to speak. So when you have a triangle that has 3 acute angles, meaning all 3 angles are less than 90 degrees, we call this an acute triangle. When you have a triangle that has 1 obtuse angle, meaning greater than 90 degrees, we refer to that as an obtuse triangle. A triangle with an angle that is exactly 90 degrees, in other words, a right angle, is called a right triangle. And the last one is rather unique because it is one of a kind. There's not different variations of it. It can only happen one way. And that is when you have 3 congruent angles, all 3 are the same, in which case we call it equiangular. A weird word to say. Equiangular. In other words, all 3 angles are exactly the same. We'll talk here shortly. Equiangular triangles have an exact measurement for those, but I don't want to spoil the surprise as to what's to come on the next page. So the diagram here, if we were looking at this picture, we're going to classify each of them based off of their angles. Let me highlight that there so it stands out. As we look here, the first one is triangle CDE. So if I'm following those corners around C, D, E, it would be a right. And we know because that little box there says there's a right angle. Next one on our list is BCE. So if I trace that, BCE, obtuse. So where angle C would be in that triangle is certainly greater than 90 degrees. What about triangle ABE?
Congruent angle.
All congruent. Equiangular. It feels weird coming out of your mouth. Equiangular.
That's what I just put on.
Recording in
Okay, just put congruent.
For now, it'll be okay. It will mean something different in the next unit. So we'll want to make sure we can differentiate between the 2. For now, I would still accept that though. Fourth one there is triangle BDE.
That'd be obtuse.
It would be. So that one's a little bit deceiving because there's a lot going on there at E. But if you think about the angle BED, that one is clearly an obtuse angle because it is larger than 90 degrees. And then the last one is CFE, which is kind of nestled in here. Sorry, it would be an acute angle, acute triangle. Good. So if you were looking solely at the angles of the triangle, you could define them as one of these four options. Of course, the equal angular one being very unique, so certainly less common. Now, alternatively, there is another way to refer to triangles, and that is based upon their sides, the unique relationship that their sides share. So we're going to start with the more special case, which is if all three sides are exactly the same length, in other words, three congruent sides, we call this equilateral. If you have only two of the three sides are equal to each other, this is what's known as isosceles. And this one will come up quite frequently. We'll use isosceles triangles quite a bit today. And then the last one is if every one of the three sides is something different, at different measurement. This is what we refer to as scalene. Now, if you're sitting there thinking, how am I ever supposed to remember all these different terms? Again, test or open note. This page alone has a lot of very valuable information now. So taking a look here at the diagram, classifying them by their sides this time. First one we have is triangle JKM. So the big one, the whole thing.
It has two, so it means it's isosceles.
Well, careful though. So here's the misleading part. When you're saying two, are you looking at these two notches right here? So that one, that is only talking about from J to N. JKM is including this whole side. So I don't think, so this one is different than this one, which there's nothing saying that this is the same as either of them.
So it has none.
None of them. So none of them are the same. It would be scalene. Second one on our list, triangle KLN is nestled in there. Notice how many little hash marks are on the sides. That does make a difference. What's that? So we got to be careful though. I'll zoom in on this one here. So based off of how many there are, that's how they're paired. So the single hash marks, those are all the same. Wait, am I looking at the wrong one? No. KLN is this little one nestled in here. And here, only these two are the same. This third one is different.
So it's two.
It's two congruent
So it would be
sides.
isosceles.
It would be isosceles. So the hash marks are, they tell you what are congruent, but also if there's multiple pairs of congruent sides, you add just an extra one to differentiate. Yeah, just simply having any hash marks doesn't mean that they're all congruent. There's different sets there. And then the last one,
Equilateral.
JKN, is equilateral. Good. So you can define a triangle typically one of two ways, and most commonly using both methods, to be very specific and kind of painting a picture for someone who could be working with what you're trying to look at as well. So what we're going to do here real quick is we're going to take a look at these triangles, and we're going to classify it both ways, both by their angles and their sides. So we're going to use two descriptive words for each. Bring this up here. So I don't know. Let's define it by the angle followed by the sides first and just try to stay consistent. So number 9, it would be a right triangle. And what about its sides? Isosceles. So right because of the 90-degree angle, isosceles because it has two congruent sides. What about number 10? Obtuse because of the angle greater than 90 degrees. And what about its sides?
Scalene.
We have to say scalene, and here's the reason why, Jonathan. It looks like it might be isosceles, but can we go by looks alone?
No.
No, we either need to have something clearly stated or some sort of visual representation on the diagram itself. So unfortunately, there's not enough information to say that it is isosceles, so we have to go scalene. What about number 11? Equiangular?
Yes.
And equilateral, I heard. It's not a coincidence. We'll talk later how the fact that it is equiangular forces it to also be equilateral. But again, that's in a later lesson. What about number 12?
The right angle.
So again, it may be tempting to say that, but
Obtuse.
okay, if it was obtuse, one of these angles would have to be greater than 90 degrees. And I'd say it's too close. I'd want to say acute.
Yeah.
What about the sides? All three are different. I'd say scalene. Number 13.
That's gonna be a right angle.
That is definitely a right triangle because of the right angle. And what about its sides?
Scalene again.
We'd have to say scalene because there's nothing there telling me that any of them are congruent. And then the last one.
Right angle.
Ooh, careful. Double check that measurement. It's greater than 90.
So she's right.
It would be obtuse. It's close, but unfortunately, geometry close isn't close enough.
And then scalene.
Ooh. So this one's sneaky because instead of the hash marks, it actually put measurements there for you. And if you notice that the two measurements they gave us are both 5 feet. So it would be isosceles.
That one got me too.
Yeah, so we get so used to seeing the little hash marks there. Be
Yeah.
mindful that those hash marks are really just a shorthand way of saying these are the exact same measurement.
Or if we see the measurements.
If we see the measurements and they are the same, then we could, if we wanted to, put the hash marks there as well. Yeah, absolutely. Good. So classifying triangles, not too bad. We can really add some descriptive language there if we're trying to talk about what type of triangle we were looking at. Now, into the more, I don't want to say that what we talked about was not useful, but more useful for us today are two theorems that are always true when talking about triangles, any triangle, regardless of their classification. So the first one is known as the triangle angle sum theorem, which states, I know it's up there in bold, but I'm going to highlight it as well because I'm extra. The sum of the measures of the angles of a triangle is 180 degrees, always. So if you add up all the angles inside of a triangle, it will always equal 180 degrees. That is a fact that we're going to rely heavily on here in just a few minutes. So in that diagram, if you took the measure of angle A plus angle B plus angle C, we know that even not knowing any of their measurements at all, I still know that whatever they are, they have to equal 180 degrees. Now, the second one actually relies on the triangle angle sum theorem in a manner of speaking. It's a little bit trickier to wrap your head around, but it is the exterior angle theorem. Now, an exterior angle is formed when you take one of the sides of the triangle, which is just a line segment, and continue going out past one of the vertices, one of the corners there, extending it out along that same line. That forms an angle on the outside of the triangle, which is called an exterior angle. Now, this theorem states that an exterior angle always equals the sum of the two non-adjacent interior angles. I'm going to emphasize non-adjacent. So there's three angles in the triangle. If you add up the two angles that are not right next to your exterior angle, it's going to equal whatever that exterior angle is. And the reason for that, if you wanted to work through the math here, is we know that if we added up, I know it's not labeled, but if we added the three angles inside this triangle, what do they equal?
180.
180 degrees. Now imagine for me, if you're just looking at these two lines, they form a linear pair, which means these two together equal 180 as well. The common piece that the two relationships have is this one. When you remove it, that's telling you that basically this must equal this, because these all equal 180. This equals 180. Remove the common piece, those two must then be equal. Again, we could do some diagrams and stuff like that. It gets kind of boring. For our purposes, if you're okay with it, we can trust this theory. And for this particular diagram, the measure of angle 1, which is the exterior angle that's been created here, would just be equal to the measure of angle 2 plus the measure of angle 3. Now, again, that is a relationship we're going to rely on a little bit here going forward as well. So all the angles inside of a triangle equal 180. Extend one of those sides out to create an exterior angle. That angle is going to equal the sum of the other two angles that's not adjacent to it. So we're not going to do every single example because they do get a little bit repetitive, but just to kind of give us that variety, we're going to jump down below here. I'm going to start with number 1. It's asking us to find all missing angles. This one, we're just looking for the measure of angle 1, which is right here. Appears to be obtuse. How would you work that out?
Would you add 24 and 37 and then subtract it from 180 or no?
Absolutely, because
Oh.
you know the whole thing should be 180. So in fact, I'm going to do what you said, but just slightly backwards. We know that the whole thing equals 180, right? If we subtract from that the 24-degree angle and the 37-degree angle, what we're left with should be our missing angle, which is angle 1. So what's 180 minus 24 minus 37?
119.
119. Good. Now, the second one here, a little bit different. Notice that angle 1 is now the exterior angle outside of our triangle. And we had that theorem up above that said that that exterior angle should equal the sum of, what's that? So the exterior angle by itself doesn't equal 180. That one combined with this adjacent angle would be 180. But the theorem up above, right there, says that the exterior angle would equal the sum of the two non-adjacent. And here we were given those two non-adjacent ones. You would just add those two together. Now, hypothetically, I could go a longer route. If I didn't trust the exterior angle theorem, I could add those two together and subtract them from 180. And that would give me this angle measurement. And then I could take that angle measurement and subtract it from 180 to get that one. It would be a more roundabout way. It would still result in the same solution. But in this one, what do you get?
128.
128 degrees. So just so we know what we're referring to here, the way we got that was from taking the 76-degree angle plus the 52-degree angle. Next one here, it's another exterior angle one, but notice where the missing angle is this time. Yeah, it's inside the triangle now. We actually know the exterior angle. We don't know one of the non-adjacent ones, but that's okay because if we still use the same concept, the same relationship, the exterior angle, which is 104 degrees, should equal the sum of the two non-adjacent angles. So that would be the, what, 79 degrees plus angle 1. How would you solve that equation?
Did you add 104 to 79?
Ooh, careful. Let me throw this up in there. How would you get that 79 away from that angle 1? You would subtract it. So yes, the relationship does deal with addition, but depending on where your missing value is, that may change how you solve for it. So I want you more focused on setting up that relationship. Don't just assume that it's always adding. So yeah, we would subtract the 79 from both sides. And what do you end up getting? 25? Good. So angle 1 is 25 degrees. So more or less, those three there at the top are probably the only three combinations you could use in a single triangle with those two theorems. Those are really the main possible combinations there. Now, obviously, we got to spice things up a little bit and throw in multiple triangles, some of them next to each other, some of them inside each other, just to make sure that we're not getting distracted and are able to focus in on what we know and ignore what we don't yet need. So, we'll try two of these. We'll do number 4 and number 6. I'll give you the answers to 5 and 7 if you want to try those on your own. I'll give you these here for you. Doesn't matter which one we find first. We've got a couple options here. What are your thoughts? What do you want to look for first? Yeah, we could do angle 1 because right now in this little acute triangle here, I know 2 of the 3 angles. And I know that that sum should be 180. So if I took 180 degrees minus 66 degrees minus 84 degrees, what's left should be my angle 1. 30? Okay. Then what? We may have to recall on some past skills. So like all the angle properties that we learned still apply here today. Technically, we do have enough information to find either. I will tell you finding angle 3 first will be a little bit easier. Take a look here. The 84-degree angle and angle 3 form a line. which makes them a linear pair. Which means if I take 84 from 180, I should be left with angle 3. So I'll make a little note up here. It's gonna feel a little bit all over the place here. So we have a linear pair. So I can take 180 degrees minus 84 degrees should equal my angle 3. 96? 96. And then lastly, I have a couple options. I could either try to work with this big triangle, which gets a little bit fuzzy because the big triangle has an angle up here that's been split into two smaller ones. Or I could go with this medium-sized triangle here towards the right because I have the 43-degree angle. I now know angle 3, which means angle 2 is just what's left from the 180. So I'll take the 180 degrees minus the 43 degrees minus the 96 degrees, which was our angle 3. And that should give us angle 2. 41. So that's not the only path we could have taken. There was some other ways we could have worked our way around there, maybe a different order to find some of those angles. But go with what you're comfortable with. Me, I always look for the big triangles. I always look for linear pairs. Linear pairs are pretty quick to spot. But just work your way through it. Like I said, I'd give you number 5's answers for you to kind of work through on your own pace. If you're trying this one out, you should get 47 degrees for angle 1, 137 degrees for angle 2, 31 degrees for angle 3. And again, if you're watching the video right now, talking into the future, you could pause this, work it out, and check your answers. So I'll skip over that one a little bit more quickly. I want to jump to number 6 here. And let's see what we can do. Which angle do you want to find first?
1.
Angle 1, okay. So I'm looking at angle 1. I notice it's in this top triangle here. I have 2 of the 3 angles, and I know what the sum should be. So working towards angle 1, we know that the sum of all the angles up there should be 180. So if I take the 180, subtract the 68 and the 61, I should end up getting angle 1, which is 51 degrees. What about angle 2? That one seems tricky. I only know one of the angles in that triangle, and that's the right angle. This one throws back to the last unit. I'm going to throw in some symbols here. Let me know why I'm allowed to do this. They are congruent, but why? Do you remember what those are called? Not quite. Alternate interior and the exteriors and stuff has to do with parallel lines. And we don't necessarily have those here. But these are not quite, because they are going away from each other. These are vertical angles. And vertical angles are always congruent. So angle 2 is 61 degrees. So now I have 2 of the 3 angles in that bottom triangle. The 90 degrees we already knew, the 61 degrees that we've kind of in a way we're given. So again, the sum should be 180 degrees. I'm going to subtract the 90 degrees and the 61 degrees to get angle 3, And I should end up with 29 degrees. That box right there. Yep, that box right there tells me that that angle's 90 degrees. These two were both 61 because they're vertical. So the 90 and the 61, we subtract from the 180. And that just leaves us with a little bitty angle 3. Last one here. Again, we're not going to go over this one. I am going to give you a quick clue though. It does say BC bisects, which means cut in half, angle ACD. So that 90-degree angle is cut in half. But that's all I'll give you on that one. I will also give you the answers. 87 degrees for angle 1, 45 degrees for angle 2, 45 degrees for angle 3. Well, there's the bisecting part. You cut 90 in half, you get 2 45s. And then angle 4 is 52 degrees. Guess that secret didn't last very long. My bad. But again, if you're watching this video, you pause, try it out, work through that diagram. It's a really neat exercise to kind of work through a picture like that.
Hey, how did you get 52 on that, Josh?
On angle 4,
Yes.
so angle 4 is right here. Knowing angle 3 and 2 must both be 45 because of a bisected right angle, you would just take, unless double check my math for me, 180 minus the 83 minus the 45.
I think I did my math wrong.
That's
Okay.
fine. I'm glad you're checking because some of these calculations, it's been a minute since I've done them, so I may have made some mistakes. All right. Woo, look at these messes. I'll pick some, I want to try to pick some of the I'm going to do I'll skip number 8. I'll give you the measurements for you to try out later if you wish. So angle 1 is going to be 64 degrees. Angle 2 is 26 degrees. Angle 3 is 36 degrees. What I want to make sure we have a chance to look at is number 9 here, which is very involved all of a sudden, but it brings back something from the end of our last unit, which are parallel lines. And they didn't really denote them here on this diagram, probably because they were tight on space, but line L is parallel to line M, which means we do have some alternate interior and exterior angles. So we also happen to have a triangle that's between them. So it gets real trippy here real quick. I'm going to suggest, though, we start with angle 1. Now, angle 1, if you imagine this line right here, and it's a segment right now, as a transversal, angle 1 and 73 degrees are alternate interior angles. And alternate interior angles are always congruent. So angle 1 is 73 degrees. Angle 2, well, I have a way I could do this, but I'm not even using triangles yet. Angle 2 is part of this really big linear pair. So I could actually subtract angle 1 and this 49 degrees from 180 and be left with angle 2. Now that one's a little bit hard to see. So I'm going to hold off on that one. I'll come back to angle 2. I'm going to jump over to, I'll jump down here to angle 3. Here's an easier to see linear pair. So 3 and 73 degrees, angle 3 and 73 degrees should equal 180. So if I subtract the 73 degrees from that, I should get my angle 3, which is 107. Yep, 107. Still going to skip 2, and I'm going to jump over to angle 4. Now this one's a little bit easier because if I imagine this side of the triangle as a transversal, angle 4 is an alternate interior with this 49-degree angle, which means angle 4 is 49 degrees. Now, if it makes you feel better, we can go back to angle 2. Now that I know the 73-degree angle and what angle 4 is, I can take those two results, pull them from 180, and what's left is angle 2. So I'm going to squeeze that in up here. 180 minus 73 minus 49, which was our angle 4, was what?
58.
58. Actually, I should do this. This equals angle 2. Angle 2 is 58 degrees. And then last but not least, we have another linear pair down here for angle 5. 4 and 5 form a line. So if I take 180 degrees minus 49 degrees, which was my angle 4, I'm going to get angle 5, which leaves me with, I believe, 131.
Yes.
Okay. How are we doing on time? 118. I'm going to skip 10 and 11. I'll give you those answers here real quick. They're a little bit challenging, so if you do get stuck and if you're trying them out later, come talk to me. If you get stuck on your assignment, I'm always here to help you as well. But for this one, number 10, angle 1 should be 34 degrees. Angle 2 should be 52 degrees. Angle 3 should be, oh boy, I think I have 38 degrees written down. Angle 4 should be 94 degrees. Angle 5 is 56 degrees. And angle 6 is 38 degrees. On number 11, angle 1 should be 62 degrees. 2 should be 71 degrees. 3 should be 109 degrees. 4 should be 35 degrees. 5 should be 109 degrees. 6 should be 29 degrees. 7 is 47 degrees. And 8 is 62 degrees. And again, if you miss any of those, this video is going to be posted today. So at any point, feel free, if you want a little mini exercise, you're welcome to take a look at those. Scared me. All right. What I wanted to do is I wanted to get down here and I wanted to do 2 of these examples. think I'm gonna do 12 and 14. It's asking us to solve for x first, then find each of the angle measures that are listed there. So that's really all three angles in the triangle. Now, if you take a look here, those are all angles inside the triangle, and they all have an x in them, which is intimidating at first until I remember that there's a very specific relationship here. What do I know to be true?
It all equals 180.
Yep, all three of those added together has to equal 180 degrees, which means, very carefully, doesn't matter which one I start with, I'll start with D. If I take angle D, which is 5x minus 2, plus angle E, which is 9x plus 3, plus angle F, which is 11x minus 21. I know because they're all three angles in the same triangle, I know that they have to add up to 180 degrees. Then I just go into solving mode. It's just an equation. I think I give myself enough space there. What I would do just to clean this up very, very quickly is combine as many like terms as possible. So the 5x, the 9x, and the 11x, I believe will give me 25x. The -2, the +3, and the -21, I believe, give me -20. That's still equal to 180. And then I would just go into solving. I'd add 20 to both sides. So 25x equals 200. Divide both sides by 25. And I get x equals 8, I believe. Now, how you find the other three angles is up to you. Whether you individually plug that 8 into each of their expressions and crunch those numbers, that's fine. Once you plug it into one or to two of them, you can technically find the third angle. It's entirely up to you. But if you were to do that, I'm going to jot this down next to it here real quick. So we had angle D was 5x minus 2. So 5 times 8 is 40. Take away 2 is 38 degrees. Angle E was 9x plus 3. 9 times 8 is 72, plus 3 is 75 degrees. The angle F was 11x minus 21. So 11 times 8 is 88, minus 21 is 67. And that again is all thanks to the fact that we now know what 8 is. So we just plug them into each of those expressions. So it's not exciting work. It's a lot of just number crunching, a little bit of equation solving. Realistically, the newest part here today is just setting up that relationship, knowing that all those angles had to equal 180 degrees. That was really the new thing. Everything else is just solve. Next one here, I'm going to skip number 13, but I will give you the solutions there. It's very similar setup to number 12. For X, you should get 13. Angle P then will be 126 degrees. Angle Q would be 30 degrees. Angle R should be 24 degrees.
Is that equal to 180 degrees?
Yep, all three of those added together should equal 180. which will give you the equation to then solve for x. Yep. So like almost identical setup to the one above it. I do want to take a look at number 14 though, because instead of all three interior angles, we have that exterior angle again. So this uses the second theorem that we introduced today. And that second theorem said that if you have an exterior angle, which we do here at angle BCD, the 18x minus 15, that is going to equal the sum of your two non-adjacent angles. So 18x minus 15 is going to have to equal these two added together. So I write it out just like that. 18x minus 15 equals 13x minus 11, which is angle A, plus angle B, which is 4x plus 1. And then I go into solving mode. So if I was going through this one, I would do the like terms first here on my right-hand side. 13x and 4x give me 17x. Negative 11 and positive 1 should give me a negative 10. Get my variable to one side. So subtract 17x from both sides. Get x minus 15 equals negative 10. And then add 15 to both sides. I get x equals positive 5. Just like before, though, once you find that x, it's going to help you find some of those other measurements here. One of them is going to require a little bit more of a thought process we'll talk about here in just a moment. So let me come over here to my answers. We just said x is 5. And from the diagram, we had an expression for angle CAB that was 13x minus 11. 13 times 5 is what, 65, I believe. Minus 11 is 54. Angle ABC, that was our 4x plus 1. So 5 times 4 is 20 plus 1 is 21 degrees. ACB, we didn't actually have any expression for that one, so I'm going to skip over to DCB, which was our exterior angle, the 18x minus 15. Five times 18 is 50 plus 90, I believe.
Yes.
Take away 15
75.
is 75 degrees. So how am I going to find ACB? Which is right here. Give you a clue. Angle ACB and DCB are a linear pair. Which means if I subtract the 75 from 180, I should have what's left. It's 105 degrees. ACB. Guess I should squeeze that in there. 180 degrees minus 75 degrees. All right. We're on a roll. doing fairly well for time. Let me give you the last ones here. Again, if you wanted to try this last exercise, very, very similar setup to number 14. All that's changing is the values. You should get 17 for X. Then angle JKL should be 87 degrees. Angle KJL should be 58 degrees. KLJ should be 35 degrees. And KLM should be 145 degrees. So again, same setup as 14. The exterior angle has to equal the sum of the other two, the two non-adjacent angles. All right, last page for today. Taking a closer look at two special types of triangles. That is the isosceles triangle and the equilateral triangle. Actually, that's funny. We're not looking at equilateral triangles. We're just looking at isosceles triangles. Wrong title. Okay. So isosceles triangles, these are the ones that had two congruent sides. There's a really cool relationship here that also tells us then something about two of the angles as well. So parts of an isosceles triangle, looking in this diagram here, two congruent sides are called legs. Just what someone decided to call them. So in this case, those two congruent sides in this diagram is that AB, side AB is congruent to side BC. Those are my legs. The angle where those two sides intersect is called the vertex angle. So the angle formed by those two sides in this case is angle 1. The side opposite the vertex angle is called the base. So in this case, the base is the only side we haven't talked about yet, which is AC. And then the angles along the base are called base angles. So that was a really roundabout way to get to something that we're going to look at a lot, which are base angles, which in this diagram here are angles 2 and angles 3. Now, that vocabulary was necessary then to help us with describing these two, actually one theorem and its converse, meaning its opposite. So the isosceles triangle theorem says that if two sides of a triangle are congruent, aka an isosceles triangle, then the angles opposite those sides must also be congruent. So in the diagram above, basically what that's saying is if side AB, which is one of the legs, is congruent to side BC, which is the other leg of this isosceles triangle, then if we know that to be true, we've already been told that, then we can automatically jump to the conclusion that angle 2 is congruent to angle 3 without any other notation or anything. If you know the sides to be congruent, their opposite angles must also be congruent to each other as well. Now, that's not saying that the angle measurement is congruent to the side measurement. Those are two different relationships. Sides are equal to each other. Separate from that, the angles then must be equal to each other. Now, the converse says the exact same thing in reverse. So if you knew it the other way around, if you knew or were told that angle 2 was congruent to angle 3, then with absolutely no other information other than this fact, you could safely say that side AB must also be congruent to side BC. So it is saying if one, then the other, but then vice versa. So if you know one, then you know the opposite to be true. Excuse me. So we're going to try a few out here using this unique relationship that isosceles triangles give us. Starting with number 1, where the instructions are to find each missing measure. So we are looking for angle J, angle K. All we know is that angle L is 68 degrees. So let me hear your thought process. What do you see? What do you know? What are congruent?
Wait.
What you said is true. I just need to know what you're talking about. Something is congruent here. JK and KR are congruent. So could we say that this is an isosceles triangle? Yep. Well, if those two sides are congruent, then I happen to know that two angles must also be congruent, which in this case would be angle J and angle L. So I already know what angle J's measurement is, 68 degrees. But how do I figure out the third angle? Sorry, Jonathan? Subtract both of those from 180. We know that the total sum should be. So 180 minus 68 degrees minus another 68 degrees. So 44. So we get 44 degrees. Again, I presumptuous here. Let me. Good. It's really nice when if one thing's told to be true, we can already assume something else to be true. Let's take a look at this other one here. Ooh, this one's a little sneaky. Let's focus on what we know, though. We're looking for angle C and E. We know angle D. What else do you know about this triangle?
Legs are congruent.
We have two congruent legs, so we have another isosceles triangle, which means that there's a pair of congruent angles. What angles would they be in this case?
C and E.
C and E, the angles opposite those congruent sides. So C is equal to E. Well, unfortunately, I don't know either of them.
Did you take 180 minus 106?
Well, let's see what that gets us. 180 minus 106 equals what? 74. Now, if I were to make both of those angles 74 degrees, I think I'd run into a problem
Yeah.
because that'd be too much, right? That'd be greater than 180. But here's the thing. You just told me what was left. These two together should be 74. But if they also have to be congruent, what am I going to do that 74?
Well, okay, I divide.
Divide by 2. Because if they are both the same, cut 74 in half to share with those two angles. You've got your result. What'd you get? So 37 degrees. So both of these would have to be 37 degrees. And if you're ever unsure, do a quick check. Do 106 plus 37 plus 37. You should get your 106. Last one in this little subsection here, slightly different approach because this time it's not just asking for angles. We're actually looking for one of the side lengths and measure of angle Y. So do I know right off the bat, like immediately, do I know that this is an isosceles triangle?
Yes.
How?
7.
Oh, you cut out. I see you talking, but I don't hear anything. I'm guessing you were talking about the 77s. Okay. So the fact that they're the same, another word for that would be congruent. If you have two congruent angles, their opposite sides must also be congruent. So I could say that XY and YZ must also be congruent. Because remember, the converse of that theorem up above said it's not just true one way, it's true in reverse as well. So what's the measure of YZ? 12 centimeters. And then how am I going to find the measure of angle Y?
77.
Just once?
Twice.
Twice. So 180 minus 77 minus 77, I think I heard 26. Good. All right. I think, let me see here. I'll do two more with you. Just because these last two have you setting up an equation, but they're pretty repetitive. Like 4 and 5 are pretty much the same. 6 and 7 are pretty much the same. So I'm gonna take a look at number 4 here. We're finding the value of the variable, just the variable. What can we set up here?
Well, then we go to 180.
Careful. Being congruent doesn't necessarily tie into being 180. I know that all three angles are 180, but I don't even know anything about that top angle. What can you tell me about the two angles where we have the expressions?
They're equal.
They are equal. Because if you look at it, if we have two congruent sides, those angles that are opposite them must also be congruent. That was from the theorem above. So if that is true, then 5x plus 9 must therefore be equal to 8x minus 30. And then I just solve. Get my variable to one side, subtract 5x from both sides. I get 9 equals 3x minus 30. Add 30 to both sides. I get 39 equals 3x. And lastly, divide by 3. I'm going to do a double step here. I'm going to write my x first. I know 39 divided by 3 gives me 13. Okay. So knowing that we have two congruent sides tells me that the two opposite angles must therefore be congruent to each other as well. That is the same relationship you will use in number 5. Number 5, if you solve that one, you should get that x equals 8. Again, same setup. So I won't.
So, sorry, we're just finding the x values and we don't have to go no further.
Correct. So this set of directions only said find the value of the variable. Now, theoretically, if I said, okay, go back and find more things, once you have that variable, you just start plugging them in and going. On these, though, just need the variable. So that does make me think, make sure you read the instructions carefully so you know exactly what it's asking for. Number 6, basically going to be the same thing in reverse. This time we have a pair of congruent angles, which excuse me, I should have a pair of congruent sides, which thankfully are the two sides that I have expressions for. So I'm going to set them equal as well. Was that what you're?
Yeah.
Okay. So in this case, 15x plus 7 must equal 23x minus 17. So get the variable to one side. I'm going to subtract 15x from both sides. I believe that gives me 7 equals 8x minus 17. Add 17 to both sides. I get 24 equals 8x. Divide both sides by 8. Should get x equals 3. So, like I said, number 7 is very similar to number 6. The only difference is instead of putting the little arcs in the angles to say they're congruent, they put 2 of the same measurements in there. Same relationship, you're going to set them equal to each other. If you wanted to try that one out, you should get that x equals 16 on this last one.
So you don't use that 74 for anything. It's just
Correct. So you could use those 274s to help you find that third missing angle, but it's not even asking for that. The 74s are just important because that tells me that they are congruent. They don't actually serve any other role to help find x other than set me up to set those two expressions equal to each other. So yeah. So I guess long story short, if I were to summarize some of the things today is, I think for the most part, you guys could almost guess how to set up the equation. Either they're all going to add up to equal 180, or they're occasionally going to be set equal to each other, you know, things like that. What I want to challenge you to do, though, is before you jump into solving the equation you write, make sure that if I came up to you and said, why'd you set those equal to each other? Or how you know those equal 180 degrees? Make sure you're confident in your response, that you know why you did that. Don't just hope for the best. If you're not sure why you're doing it, come ask me. Let me know. Because it's important to know why you set up equations the way that you do. So, all right, time for the assignment.